All right, good morning. This is the beginning of the recording. Got about 61 seconds here. Alrighties, folks, welcome back. I'd like to take a look at these two warm-ups. They help set the stage for kind of where we're headed today, I hope. The first of these, integral or antiderivative of 3 times t to the 10th dt. If the t here and there bother you, then of course you could just replace both of the t's with x's. You could replace both the t's with u's. It's just the name of the variable that we're using here. There's not a whole lot of work to show for the first one, so just to, I guess, illustrate a step, if you really wanted to, you could bring the 3 in front first. So if you have a constant times a function for this antiderivative problem, you can have 3 times then antiderivative of t to the 10th. And to take that antiderivative, t to the 10th, so variable raised to the exponent, we have to undo the power rule. So that's why we have now variable raised to the power is raised up by 1, and then you divide by that new exponent. So 3 times t to the 11th over 11, then plus c. The key thing about this specific warm-up question is that there's no substitution at all. Right? So there's no u equals any of that kind of business. This new thing did not happen. For the second warm-up question, for antiderivative of 1 over 3x plus 10 dx, sometimes people try to do this without substitution, and if you think about it for a long time, it might be possible, but I don't think it's worth it. I think the thing to do here is to say, yeah, let's do a substitution for this second question. Trying to do this without substitution, people usually end up making a mistake. So we'll do u is equal to 3x plus 10. Now, this seems a little strange because so far you've heard this comment that for picking what u should be, if you take the derivative of u, I'll just reveal it, right? The derivative of u here is 3 because the 10 differentiates to a 0. You should try to see if you see that derivative elsewhere in the problem. Now, the thing is the 3x plus 10, that already accounts for the 3. So that's not a 3 elsewhere. You maybe in the numerator were expecting to see a 3. So this seems a little strange. It does not, I guess the point is it does not fit the format of the hint that was given in the past to say, usually if you see the derivative of u elsewhere, and I'm trying to emphasize elsewhere in the problem, then that's usually a good choice for you. And so this seems a little disturbing that this selection of u, which I'm trying to get at, is actually going to be a good choice for you. This seems to not be a good choice here, maybe, at least following our hint. But what I meant kind of in the past is, the thing is, if you have a constant, that's usually not going to be a problem. It'll usually push out in front of the integral anyway in some form. So I guess this is to say that even the hint, this thing of like, if you pick u and then the derivative of that is elsewhere in the problem, that it's usually a good choice. Yeah, it's usually. So it's not 100% of the time, maybe 90% of the time. So there's some strange things going on here. We'll see how this works out. Let's solve for dx, meaning we need to first multiply by dx on both sides since it was in the denominator. So you have du is equal to 3 times dx. And then one last step to solve for dx is divide both sides by 3. So you have du over 3 is equal to dx. Now, I made a copy of the original question here just because we had this discussion in the way. And we'll make some replacements. Yeah, so the 3x plus 10 that was in the denominator has been replaced with a u. There's still the integral sign written. Okay, and then the dx that's right there has been replaced with du over 3. So it looks like this. It's kind of all compact like that, but I actually think it helps visually to expand this out, write this a little differently. So I'll write the number stuff first. Now this 3 is in the denominator, so you'll notice what's written here is an integral sign still, and then this is just juggling the order of things, so that's why there's still an integral sign. A 1/3. Sometimes people actually write just a 3. This should be a 1/3 though, right? Because a 3 is in the denominator. The u's still in the denominator. The du, which was written in the numerator of fraction, I think it looks a little funky there, so I just wrote the du off to the side. So we have integral sign, 1/3, 1 over u, du. Okay, now if you want to bring this 1/3 in front, okay, but I didn't write that step in. The point is, let's copy the number 1/3 and then anti-differentiate 1 over u. So that's so 1/3 times, and then the antiderivative here is ln of absolute value of u plus c. And then the original question, number 2 up here, didn't have any u's in it. So now that we've completed this antiderivative, here's where we should now replace the u with 3x plus 10. Looks like that. I think the key thing I want to say about comparing the two warm-up questions is not every anti-differentiation problem requires substitution. So there are these two integral problems or these two antiderivative problems. And this first one, there is no u equals, like, so let me just draw a line here, right? Like above, in this part right there, there's no u anywhere. So this u substitution thing, it doesn't always apply. And the reason to state this now is sometimes, this is our third day on substitution, and sometimes people get in this habit where they're like, okay, I've got a u equals for every single problem. And please keep in mind that on Monday, we had not discussed substitution at that point. And we were looking at problems that look like this. And if you get in this sort of habit of this rut that every problem should be a u equals, then you'll get stuck on some of these. So that's what comparing these two warm-up questions is about. And in fact, so like in question 1, yeah, like we could have even skipped this bringing the 3 in front, and had we skipped writing this middle step, we'd have just directly gone from here to talking about what the antiderivative is. And in fact, in the second question, there was anti-differentiation anyway. So I highlighted as I reveal this text. Even the ones that require substitution eventually require anti-differentiation. So we went from this step in red to that step in red. That's the step of finding an antiderivative. So you got to find an antiderivative anyway. It's just a question of, does it happen more or less immediately, like in the first warm-up question, or does it happen somewhere in the middle of the problem, which is what happens with substitution? Just a round of announcements. Today's a Thursday, so please complete the online quiz. I would strongly ask you to start WebWork 37. I know that's not the one that's due today, but it's the one that I want you to start today. The office hour times are listed here again for your convenience. If these times don't work, send me an email. We'll set up an appointment based on when we both have time free. And then this slide is a copy, so just a reminder that what's going on with substitution is we're undoing the chain rule. So substitution is about, you have this integral, in other words, this antiderivative problem, derivative of what is what was presented, and if the thing that had to have been differentiated was differentiated using the chain rule, we're trying to figure out what the inside function was, and so we're trying to pick what u is. And this is a challenging step, right? Picking what u is, and that's why this hint is here. It doesn't always apply, as we even saw in the warm-up, but typically if what you pick for u, if you see the derivative of that elsewhere in the problem, that's usually a good choice. Then you compute the derivative of u, you solve for dx. That first step of solving for dx always involves multiplying by dx on both sides. You'll see that as you write that down. And then replace that choice that you had up there with a u, and then in addition, when not in the step, replace dx with what you solved for in the previous step. And then your hope is that using valid algebra, that everything that needs to cancels. So cancel what you can. You're really hoping all the x's go away, because if they don't, you've got this mix of x's and u's in the problem. And if so, then your substitution is successful. If not all the x's go away, maybe go back to step 1 and pick a different u. Maybe if you've done that a number of times and it's not working out, maybe what actually needs to happen is don't do substitution, right? So that's like what one of the warm-up questions is trying to address, that not all of these require substitution. And in fact, if you just think substitution kind of wrongly for a problem, think that it should be done by substitution, but in the end it shouldn't, you'll just kind of get stuck that way. So sometimes if you kind of go around this block too many times, the thought should be, you know what, maybe it's not substitution. Maybe I got to do something else. But if all the x's go away, then you have this new integral problem that only has u's. The only variable would be u's, not u's and x's. So if it's just u's, take that integral that has just u's in it and do that integral. In other words, find an antiderivative. When you find that antiderivative, that's the step when you drop writing the integral sign, but don't forget the plus c. This step, number 6, I think is a challenging step as well. I mean, 1 is certainly challenging to come up with that guess and guess properly. But step 6 is also challenging. Finding antiderivatives just in general is challenging. And at some point, you got to find your antiderivative. So this is why I think this step 6 shouldn't be combined with step 7. Sometimes people try to do this all at once. Just do step 6, this challenging step on its own. And then once it's done, then replace the u. So yeah, this comment again, do the integral. Right, do the integral before the final replacement of u. What tends to happen, so yeah, do step 6, then do step 7, right? Like really step 6, then step 7. People try things like combining steps. People try swapping, doing step 7 before step 6. People sometimes skip step 6 altogether. This anti-differentiation step needs to be done, and since it's challenging, like do that and then do the final substitution. So I would like to try this method that we talked about yesterday and the day before, but on a much more challenging kind of question. So I'd like to look at integral of x cubed times square root of x squared plus 1 dx. We'll do this as a group. So here's the thing. I mean, first of all, now that we had that kind of warm up, my first thought, I want your first thought to be, wait, can I just apply one of those anti-differentiation rules from prior to learning substitution? If so, go for it. But I'm scratching my head, staring at this, going, the derivative of what is x cubed times root x squared plus 1? Going, don't know off the top of my head what that is. So this probably does require substitution. Okay, so what should u be? Now this seems like a very strange choice. I'm going to go with u is equal to x squared plus 1, and I'm going to promise you right now that this works. You might say, how is this going to work? Your thought might have been u equals x cubed, and you might have picked u equals x cubed because you're like, well, the derivative, if you did pick u as x cubed, the derivative would be 3x squared, and ignoring the 3 of the 3x squared, you have an x squared, and you're thinking, oh, that x squared I see elsewhere in the problem. The problem is that x squared is not going to cancel with the x squared plus 1 inside the radical, because there's a plus 1, so the pluses prevent cancellation, and it's stuck inside a radical anyway. I mean, there's lots of kind of reasons. You can try writing it out. You should certainly try it, but u equals x cubed is actually not going to work for this problem, but strangely enough, u equals x squared plus 1 is going to work. And you might say, wait a second, how's that going to work? Because the derivative of u is 2x, right? X squared differentiates to a 2x. The 1 is a constant, differentiates to 0, so I didn't write the plus 0. And you're like, I don't see, so again, sort of the 2, not worrying about that too much, I'll probably push in front of the problem anyway. But the x, like, where's the x? And you can kind of see maybe part of that in an x cubed, but you're like, this just seems like it's not going to work out, but let's just kind of see this through. Let's solve for dx. So the first step in that process of solving for dx, as always for these kinds of equations, is to multiply by dx on both sides. So you have du is equal to 2x times dx, and then divide both sides by 2x. So are we okay so far? I mean, maybe you're not happy with the choice of u, but like, are we? Let's just pause for a moment, see if we're okay with u. I have u is equal to x squared plus 1, based on looking at part of the problem up there. And then in the end, after computing a derivative and solving for dx, I have du over 2x is equal to dx. Okay, with this discussion in the way so far, especially if somebody's going to download the slides and maybe doesn't have a chance to hear the audio, what I've done is I've recopied the question down here so they can kind of follow in order our discussion. And so sorry for recopying this, but I tend to do this, when I write on the board anyway. But let's substitute what we can. So this is substitution only, so that's why the integral sign is still written. We're not ready to discuss what is the antiderivative yet, so we write the symbol as a reminder of antiderivative of. X cubed is still written. Inside the radical, this x squared plus 1 was replaced with a u, so the radical sign still needed to be written. The dx was replaced with a fraction du over 2x. So just some replacements. We replaced inside the radical, and we replaced the dx. Okay. Just a reminder that x cubed means x times x times x, and also this 2x in the denominator, I mean 2x, they're not glued together, it's 2 times x. So these are all factors we can replace, oh, sorry, not replace, we can cancel a factor of x on top and bottom. So we'll do that. We'll cancel an x on top with an x on bottom. I also just slightly shuffled how things are written because again I think sometimes the du written in the numerator of a fraction looks strange. I just shoved this off to the side. Same deal. The 2. Don't put the 2 in the numerator accidentally. So it was a 2 in the denominator. That's why you see a 1/2. It's not that the x cubed turned into x squared. Let's just clear up that it was a factor of x on top and a factor of x on bottom canceled. That's why there's an x squared now. So I hope that looks okay, at least as far as canceling an x on top and bottom, and then otherwise juggling where everything was written, just juggling the order a little bit. So it's just kind of more kind of typical of integral sign, then fixed number, then other stuff, and then the d whatever thingy last. So the main thing that happened was a canceling of an x on top and bottom. But what's the deal now? Do you see a problem? What do you notice? This is a question for the whole class. Like what's the deal? Are we happy with this? Are you unhappy with this? Any thoughts? Shrug emoji. I mean, are we okay with this? Do we move on to the... There's still an x in the integral. Gah! Right? Look at this. This is a mix of x's and u's. That doesn't sound good, right? And so normally, using the steps that were on the previous slide, this would be like okay, select a different u, but we're going to try something else. Okay? So here's the thing. There's an x squared here. Notice up here, we have u is equal to x squared plus 1. So here's what we're going to do. Yeah, not all the x's went away, but from our choice of u equals x squared plus 1, I would like to take this equation and subtract 1 on both sides. So you're going to have u minus 1 equals x squared, right? If you take this equation and subtract 1 on both sides. Now, of course, you could take this equation and solve for x if you want, but I'll introduce a plus or minus. I don't even want to bother solving for x. I have x squared right here. Let's say we've solved for x squared, and I don't want to go any further with this equation. I just want to apply this. Take a look. Over here, that question, I just copied it down again because now this discussion is getting in the way, so I copied this over here. Let's replace x squared. So right here in the middle there is an x squared, and we can replace x squared with a u minus 1. Now, when replacing x squared here with a u minus 1, you got to have parentheses because of order of operations issues. I don't want this to accidentally say 1/2 u, then minus 1 times root u. So it's order of operations. This replacement is going to require parentheses. Are we okay with that step? This is kind of a strange new thing. We've not done a thing like this. But we were sort of in this uh-oh situation over here. There was this x squared. We were hoping that after valid cancellations that all the x's would go away, but that didn't happen. So, but we were fortunate that in this equation here at the top, we could solve for x squared and then replace x squared with u minus 1. So that's what happened from here to here. Now the awesome thing that happened though is we went from a problem that had this mix of x's and u's to an integral problem that only has one variable, that only has u's in it. There are lots of ways to take next steps. There's lots of valid ways to do the algebra next, but here's what I chose to do. I put the 1/2 in front of the integral sign, right? So that's fine, like that, okay. Just bringing a fixed number in front. I also chose to write the root u as a u to the 1/2 power. These are some choices that I made. There's other ways to do this. And then for the next step, I chose to distribute u to the 1/2 power to both the u and to the 1. Now, if you distribute the u to the 1/2 first to the u and you multiply those things together, you're multiplying things with the same base. So you need to add the exponents. So this hidden exponent of 1 here and the exponent of 1/2, got to add those together, and 1 plus 1/2 ends up being the 3/2 exponent that you see right there. The next one, when you distribute to the other terms, you've got u to the 1/2 times 1. Well, there's not much to say about times 1. You get u to the 1/2. And the minus sign here comes from the distributive law. Okay, and then look, the thing is, when you have in your integral, you have a plus or a minus sign. That's great. You've got terms, right? Terms are separated by plus or minus signs. Just like derivatives, you can do one term at a time. Antiderivatives, we can do one term at a time. If it was a multiplication, we'd be in trouble. But since it's a minus, we can just do one term at a time. And now just like in the warm-up, at some point you need to antidifferentiate. So we'll do that. We're undoing the power rule, so this exponent of 3/2, you have to raise by 1 to undo the power rule. So 3/2 plus 1 ends up being 5/2, and you divide by that new exponent of 5/2. Same deal for the next term. U to the 1/2, take that exponent of 1/2, raise by 1 to 3/2, divide by the new exponent. What I chose to do was I just kept the 1/2. Since it's outside, I just inserted a set of parentheses just to make sure we've got clarity about where the 1/2 applies. And then since we've computed now and we're reporting the antiderivative, I put this plus c there. Okay, but we're not quite done, right? So now that we've done this, we've computed an antiderivative. The original question didn't have u's in it. The original question had x's. So we need to go back and replace the u's here and here with x squared plus 1. And we'll have a thing that looks like this. So it looks kind of big and messy, but the last step isn't so bad, right? The replacing of the u. It's this other stuff that was kind of strange. So I want to just pause. We are done with the question, but I just want to usually there's questions. So I want to make sure there's a lot of little pieces to the process, in fact. So if you have a question, you should ask it. It's usually going to be a short answer. And that's not a reason to not ask it. It's all the more reason to ask it. It's not going to take us a lot of time to answer the questions. There's just so many little things. It's easy to have missed something in the process. So we have questions that can be addressed about, wait, how did you get from this step to that step? Anything like that. If I'll wait a little longer for another question, but otherwise, do you want to see another one of this type where kind of looks like we got stuck, but then we won't? Can you? Sorry, I see a comment coming in on one screen, but not the other. So I gotta hang on just a second. I gotta hit the chat box here. Okay, can you explain how you got u to the 3/2 minus u to the 1/2? Yeah, sure, certainly. Sorry, it showed up on one screen, but not the other. Yeah, so the question was, can I explain where did that come from? That's the question. So what happened was I took right here this u to the 1/2 and I distributed it to the u and to the 1. Right? So this would be like if you had, just for totally different scenario, but if you had like b minus c times a, then you can distribute. I know that normally the a would be written on the other side of the parentheses, on the left side, but this would be ba minus ca. And the point is, in this case, the b would be like the u, and oh geez, why is this? Okay, so in this case, u minus u minus 1 uh, to the and then times u to the half would be u times u to the 1/2 minus 1 times u to the 1/2. So first of all, right here, you're multiplying two things with the same base. I mean, I'll add in that right in that hidden exponent of 1. Multiplying two things with the same base, you've got to add the exponents together. So you'll have u to the 1 plus 1/2 minus, and then 1 times a whatever. I'll just not write the 1 times, so I have u to the 1/2 here. And then the whole point is this 1 plus 1/2 can be written instead as 3/2. Does that help address that matter? I'll check this screen, I guess, because that's where the and then while I'm waiting on a response for that, are there other questions we can address as well? I hope that addresses it. Okay, cool. I got a yes for that. Other questions? Is it time to see another one? I'm going to go with yes. All right. So how about this? Integral of, or antiderivative of, x times root 2x minus 1 dx. I'm going to select for u that 2x minus 1, the thing that's inside the radical. The derivative here is just a 2, right? Because 2x differentiates to 2, and then minus 1 differentiates to minus 0. I just didn't write in the minus 0. To solve for dx, our first step is to multiply by dx on both sides. So du is equal to 2 times dx, and then divide both sides by 2. So you have du over 2 is equal to dx. We'll take the original question at the top. Substitute, let's replace what we can. We're trying to get a problem to not have x's anymore, to have u's instead. So let's see. Yeah, inside the radical was a 2x minus 1. We replaced that with a u. The dx was replaced with the fraction du over 2. And, well, nothing. Normally, after you do these kinds of substitutions, you look for anything that cancels. Here, nothing even cancels. So had this just been like our setup yesterday, it would just said, oh, give up and go back and pick a different u. But you're noticing today, the shenanigans is like there's one other thing you can always check on. So before trying over or trying something that's not substitution, at this moment, go back and look at what you have. Like if you have x's and u's still, maybe go back and look to see. In this case, we have x. In the last question, we had an x squared. So in the last question, because we had x squared, you go like, is it easy to solve for x squared? In this question, since you have x, you want to go back and go, is it possible to solve for x? And that doesn't look too bad, right? So we're gonna do that. And I hope you also. Sorry to have done it. But, we needed, I think, 2 days to just kind of try problems that don't have these strange issues in them. I didn't want the steps to they would have been too confusing. So I saved it for the third day. Let's go ahead and solve for x, right? Not all the x's went away. Let's take the u equals 2x minus 1. To solve for x, add 1 to both sides, right? So u plus 1 is equal to 2x. We still haven't solved for x. It says 2x here, so we can divide both sides by 2 and have u plus 1 over 2 is equal to x. Cool. So we'll take the most recent version of the problem, the one where it looks like we got stuck, and then replace the x that appears right there with a u plus 1 over 2. So I copied the question as we last had it, and then replace the x with u plus 1 over 2. Now, this is just a replacement. We did not find an antiderivative yet. That's why there's still the antiderivative sign. So I hope we're okay up to this step. Oh, the other thing I did in the process, not only did I replace the x, I thought I went ahead and replaced the root u with u to the 1/2. Just another way to write the radical. Okay. I hope we're okay up to there. But what this sort of like last ditch effort, this like one other, the plan B option gave us was It looked like not all the x's went away, but we tried. We just tried a little harder and solved for x and replaced it, and we got to the case of having a problem where all the x's went away, right? That's a good thing. If all the x's go away, that's a good thing. I mean, not just for integrals, but for in life. That's kind of awkward. Right? Okay. Wow. All right. Awkward turtle. Okay. All right. Good. So there's no more x's here. There's lots of different ways to take the algebra next. So the steps that you'll see I do, it's one way to go about this. There's lots of different ways to do this algebra that are valid. Of course, there's lots of mistakes people can make in algebra as well. So I'll just, for better or worse, I'm going to just try this one way. And one way to do this is you got one fraction times another. I mean, all these things are multiplied. You got a u plus 1, and then you have like a u to the 1 half. Like, there's lots of multiplication other than this plus sign here. And the point is there's a 2 and a 2 in a denominator. You can multiply those together and have a 4 in a denominator instead. I also just, instead of having the du as the numerator in the numerator of a fraction, just stuck the du off to the side. Again, there's lots of ways to do this, but what I chose to do is when you have pluses or minuses in the numerator of a fraction, not in the denominator, but in the numerator, you can split this up as two separate fractions. So you can write the fraction as u over 4 plus 1 over 4, right? U over 4 plus 1 over 4. And when doing so, you really have to have these parentheses here, right, for this replacement because of the order of operations. And then what I did it this way because it looks a little bit more like the previous step or the previous problem we did, where we're gonna distribute this u to the 1 half. So when doing that, you'll have a u to the 1 half times a u is that u to the 3 halves that we saw before. It should all be written over a 4, but just to avoid having fractions with the variable in it, I just wrote, instead of over 4, I just put the times a 1/4 just to the side of it. And then 1/4 times u to the 1 half requires less explanation. I just stuck the two things next to each other. At this point, we've got, again, there's other ways that this can look that would be valid, but at this point, I've got two separate terms, so we'll anti-differentiate each of those terms separately. The 1/4 you copy, and then u to the 3 halves, I gotta undo the power rule, so you raise the exponent by 1. So you have 1/4 times u to the 5 halves over new exponent of 5 halves, plus 1/4 times, and then to anti-differentiate u to the 1 half, this will be u to the raise the exponent by 1 to a 3 halves, divide by the new exponent of 3 halves, and then plus a c. So here's where we're doing the integral, as I say, or finding an antiderivative. That's why there was antiderivative notation here, and in this step there's no more integral sign. And then now that we've done that antiderivative, we've found the antiderivative or found the integral, at this stage, now it's time for that step 7 where we now replace the u's, because there was no u in the original question. Replace every u you see with a 2x minus 1. So that's the end of this question. Let's pause again, see if we're doing okay. See if there's questions about this one. Well, then I would like to ask if you would try this next one. It's of the same kind of fashion, and just so that normally I wouldn't, this wouldn't be given to you, but I just here, use this u. Like, this u is going to work, right? But you'll sort of notice this momentary getting stuck feature. So I'll just stop talking. We give you a chance to try it with this choice of u. U is equal to x cubed plus 2. And the problem is integral of fraction x to the 5th over root x to the 3rd plus 2. So you'll notice, kind of like the other two questions, I picked for you the stuff inside the radical. Not including the radical, just the stuff inside the radical. So I'll just reveal a couple steps here of here's my derivative and then my solving for dx. Just to make sure we're on the same page with the algebra, if I take the original question up there and make some replacements, how do things cancel validly? Well, there's 5 factors of x on top and 2 factors of x on bottom. So canceling x squared on top and bottom leaves an x cubed in the numerator. But the issue, of course, here is that not all the x's went away. I'll just stop talking again. What's this? So this x cubed is an issue, right? And so it makes sense to try to solve for x cubed. Not too bad, right? Subtract 2 on both sides from what we said u was. And then, so now x cubed can be validly replaced with a u minus 2. So the most recent version of the problem, where we were sort of stuck, or we would have said we were stuck yesterday, I replaced the x cubed with a u minus 2. So I hope you have a step that looks something like this. Okay, so what I'm going to do here is this problem, even more so than the previous 2 questions, there's lots of different ways the algebra can look. So if your algebra looks different from what I have here, I don't want you to stress out too much. And at the same time, like, I had to choose something. And I did also stylistically do things a little different than the other 2 questions, just to give like some variety of how the algebra looks. So one option is there's this 3 in the denominator, and I chose to bring it in front. Now, of course, it's not going to just magically appear in the numerator. It's still going to be a 3 in the denominator. So you'll see this 1/3 first of all. So that already takes care of that 3, and then the du, no, doesn't have to belong to part of a fraction. I just wrote the du. Finally, sort of like the last problem, there's this u over root u and the 2 over root u that I wrote separately, right? So when you have a fraction and there's pluses or minuses in the numerator, you can split this up like this, right? And the reason is because you can go backwards. If you have 2 fractions that you're adding or subtracting with the same denominator, you can combine them into one fraction. So then what? Now there's lots of approaches that you can take next, but I'm just really not a fan of having the variable both in the numerator and denominator, because this sounds like some kind of quotient rule like business, but for antiderivatives. So what do? We use some algebra to clean this up. So there's still the 1/3, there's still the du, but the thing is u over root u can be written as u to the 1/2 power. So let's explain that. So this circled thingy here and this circled thingy here are actually equal. So these are simple. So there's one way to see this is if you have u over root u. This is u to the 1 over u to the 1/2, right? Another way to write root u is u to the 1/2 power. And here what's going on is you've got 2 things with the same base, and so, but we're dividing the 2 things from each other. So we have to subtract the exponents. So you're more familiar with when you have 2 things with the same base, but you're multiplying the 2 things, you add the exponents. So in sort of reverse, when you're dividing the 2 things, you have to subtract the exponents. So you have here u to the subtract the exponents, 1 minus 1 half. And that 1 minus 1 half is why you see this exponent of 1 half here. If you don't like that explanation, here's a completely different explanation. U over root u. This is usually where the questions appear, so that's why I'm just kind of trying to address it. Another way to state this is you could replace the u in the numerator with root u times root u. Right? So u is the same as root u times root u over a root u, and then you can cancel a root u on top and bottom, and you'll have just a leftover root u in the numerator, and another way to write that is u to the 1 half. So that's two completely different explanations of why u over root u turns into u to the 1 half power. So I hope one or the other explanation, or ideally both, are like, yeah, that works. Then the other fraction after the minus sign. So the minus sign was copied. So then there was a 2. The 2 was in the numerator before, so it's still a numerator quantity here. And then, yeah, I should get rid of maybe some of these markings. Then the root u in the denominator ends up being a u to the negative 1 half power in the numerator. Okay, if that's okay, then I copied the 1/3 here on the outside. Now, this is a step where this 1/3 should apply to all the terms in here, so I just use a set of parentheses, and we now anti-differentiate each of these one term at a time. So when the exponent, undoing the power rule, when the exponent is 1 half, you got to raise the exponent by 1 to a 3 halves, divide by the new exponent. When the exponent is so copy the 2 after the minus sign, and then when the exponent is a negative 1 half, you raise that exponent by 1, so negative 1 half plus a 1 is a positive 1 half, and you divide by the new exponent. And having now completed our antiderivative, we do need a plus c here. And as a final step, the original question did not have u's in it, so now that we've computed our antiderivative, we need to go plug in, replace every u with an x cubed plus 2. So let's pause here. Are we doing okay? Any questions about this one? I think, again, the key thing that requires explanation is that turns into that. And so there's the two explanations kind of up here as a So what I'd like to do, there's not a whole lot of time left, is I'd like you to look at these. Sorry, they're kind of scrunched together. But this is kind of a mixed collection of integrals, so not all of these use this substitution thing. So some of them you're going to do a u equals. Some of them, if you do a u equals, you're just going to get stuck. So some of them you've got to like do a little algebra first instead, and then you've got a bunch of different terms. Some of them you've got to just go back to like, wait, we had these antiderivative methods before we did substitution, like on Monday of this week or last week on Thursday. So give pick. You don't have to do them in order, and if you get stuck or you want a hint, you just let me know, and I will respond to you. Okay, I see that question. Stuck on 5. So we have 3 minutes left for class, and I was just about to just do a round of announcements. I will just quickly say for number 5, and if you want to stick around after class, you can do that. But my suggestion for question 5 is is to to do this kind of business of x cubed over x squared plus 5 over x squared. Sorry, this is messy. Okay, yeah. And then using algebra, simplify each of the terms and then antidifferentiate each separately. So, um, yeah, unlike number 4, which is looking at the antiderivative of the reciprocal, um, and substitution is great for number 4. Number 5, just do a little bit of algebraic manipulations. I'll say that. I just want to do my round of announcements, and then if you want to stick around, we can work through it. I'll just say this. At the bottom of this slide, if you download the slides, there's a link. The link doesn't work yet. As in, I made a you can click on this and also you get to this like file not found page. I just haven't had time to make solutions, but I'm gonna do that. And once I make the PDF solutions, clicking on this link should work. I won't bother emailing separately about that. Just by maybe end of today or early tomorrow, clicking on that link should work. I will say that up to what we've done right now, so that this is the cutoff for next Thursday's exam. And one comment about exam 4 is I noted from the mid-April survey that some folks filled out that it was actually rather stressful to submit files for each individual question. So what I'd like to do is it will actually, I think, be better for you all. It'll be less stressful for you. It'll also organize things kind of easier for me. I think it's win-win to just ask for a single file and specifically a PDF. Now, how's that going to work? Over this weekend, one of the things I'm going to do is going to develop some resources. There's lots of free ways to make a PDF. So I'm going to give you lots of options, and you can still you can use handwritten work. There's lots of free apps out there that can do this. There's, of course, designing a Word doc. Anyway, I'll clear up, like, there's lots of options to do it, but at least I think what happens then is when submitting a single file, you get to look over that file, make sure everything looks like the way you want it to, and then turn in one file. I think that will work out easier overall for everybody. Just final reminder, it is a Thursday, so please do the online quiz, and we'll call it with that. And if you want to stick around to get this question answered, I'll do it. Otherwise, if that was enough of a hint, that's fine too. I'll just see what the response is. That was enough. Okay, cool.